Welcome back. Previously, we discussed how to solve first-order linear equations. In this video, we will instead focus on solving higher-order linear equations. Additionally, this video will review solving higher-order linear ordinary differential equations, as the techniques are entirely analogous, and hopefully, by pointing out the similarities between the two, that will help you understand both the relationship between difference equations and differential equations, and also understanding how to solve linear difference equations. So, let's get started. Let's first start by reviewing how to solve linear ODEs. So, let's review linear ODEs. So these are one general form of these is we have some coefficient ak of t times d to the k over dt to the k x. So this is the differential operator applied k times to x, and the summation all the way down to for a1 of t dx dt plus a naught of t x is equal to b of t. And I'm actually going to only use half the space here, because we'll see later that on the right-hand side we'll solve linear difference equations. So actually, let me just do that in tandem. So let's see, linear difference equations. And I'm going to use a slightly different notation from the last time, just to make things even more analogous. So here we have a k of t, x. In the previous notation, we used x sub t plus k. I'm going to do x of t plus k. But here, of course, x takes values from just the natural numbers. T plus k plus dot 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 plus a1 of t. That's the coefficient there. And x of t plus 1 plus a naught of t x of t is equal to some b of t. So, how do we solve these things? Let's recall that for solving linear ODEs, the first thing we do is we find k linearly independent solutions. To the homogeneous equation. So that's when we're setting b of t equal to 0. So let me rewrite that out just so that we're all on the same page. A k of t, d to the k of x, dt to the k, dot dot dot, a1 of t, dx dt, plus a naught of t x is equal to 0 instead. And of course, we can do the same. And so for the linear difference equations, we'll do the same thing. We will find k linearly independent solutions to the homogeneous version of the equation, which is going to be, again, setting b of t equal to 0. So a k of t, x of t plus k, plus dot dot dot, plus a1 of t, x of t plus 1, plus a naught of t, x of t is equal to 0. And we're going to call these solutions, and I'm going to use the same notation for them. Let's say x1 of t, x2 of t, and of course you can also write this without the t. That's understood that this has a dependence on t. And so let's do that here on the right-hand side, called x1, x2, all the way through xk, where the subscript here is an index over the different linearly independent solutions, rather than, as it was in the previous lecture, the t variable itself. So these have a dependence on t, but the index isn't actually t. Well then, by the superposition principle, we know that if we have some other function, let's call it xh of t, which is equal to a linear combination of our linearly independent solutions, so I equal 1 to k, of, say, ci xi of t, for all ci in the real numbers, is a solution to the homogeneous equation. And similarly, xh, which is equal to a linear combination. So this is exactly the same. I'm writing the same thing down twice. For all ci in R is a solution to homogeneous equation. Okay, and so let's actually specialize a little bit now. So in the case where these the coefficients ai of t's are constants, so if ai of t is identically equal to ai constants, then we can use the characteristic equation. Can use the characteristic equation. Let me write that in a different color. Use the characteristic equation. Let's see, this is ak lambda to the k plus dot 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 plus a1 lambda plus a naught is equal to 0. And as you might guess, in this, now that we've written it in this form, we have the exact same thing for linear difference equations. So if ai of t is equal to ai constants, then we can use the characteristic equation. Use the characteristic equation. And the characteristic equation is exactly the same. ak lambda to the k plus dot 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 plus a1 lambda plus a naught is equal to 0. Then, assuming that lambda solves this characteristic equation, of course, then we have that t to the beta, where beta is some power, we'll discuss that in a moment, e to the lambda t is a solution to the homogeneous equation, where beta is something from 0 to m of lambda, where m of lambda equals the multiplicity of lambda as a solution to the characteristic equation. Likewise, we do the same thing over here, except the solution is actually going to be a little different. And so this is where the linear ODEs and linear difference equations are differ a little bit. Let me actually put this in red to make that obvious. And here we have that t to the beta, so that part's the same. And instead of e to the lambda t, we just have lambda to the t is a solution to the homogeneous equation. And here I'm just going to copy everything again. So beta is from 0 to m of lambda, where m of lambda is equal to the multiplicity of lambda as a solution. This should be m of lambda minus 1. And this here is also m of lambda minus 1 as a solution to the characteristic equation. Okay, and so basically if something only has multiplicity 1, then you only have beta equal to 0, and so it's just e to the lambda t or lambda to the t in the case of the difference equations. Let's see, actually let me write these out. Yeah. Okay, and once we have a set of linearly independent solutions, and so this gives us k linearly independent solutions, we can, of course, use that to figure out the general solution to the homogeneous equation. Once we have that, let me extend this out a little bit further, we can do the standard thing, where we find any solution, so let's call this step 2, find any solution, xp of t, to the inhomogeneous equation, And we're going to do the same thing over here. So find any solution, xp to the inhomogeneous equation. And there are a number of different ways of doing this. So one of the ones we discussed last time, which you should is the method of undetermined coefficients. So basically guessing an ansatz, undetermined coefficients. And we did that for the first order linear equation, but of course you can do that for the higher order ones as well. So method of undetermined coefficients. And here, another one that we could use is variation of parameters, which you should recall from differential equations. It turns out there is a version of variation of parameters for linear difference equations as well, but we're not actually going to discuss that in this course. Just be aware that such a method also does exist. And once we have all that, then in step 3, we just combine them together. So then we get a general solution, x of t, which is equal to x sub h of t plus x sub p of t by the principle of superposition. And we do the exact same thing again. So, general solution, and let's say x is equal to xh plus xp. Of course, these are all dependent on t, and I'm just leaving off the dependence here. You can write it on there if it makes you feel better. It doesn't really matter. So, principle of superposition. Okay. So, just a quick review. It turns out that the primary difference between solving linear ODEs and linear difference equations is the types of ansatzes that we can use. So this guess that we make here differs between the two of them for reasons that have to do with the types of operators we're applying. And I'll go into that a little bit more in the next video, but not too much, since that should be something you remember from your differential equations class. Okay, so let us move on. If you look in Ellen Allen's textbook in definition 1.7, the solutions, the zeros of the characteristic equation, let's call them lambda 1 through lambda k of the characteristic equation. Let's say that's ak lambda to the k plus dot 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 a1 lambda plus a naught is equal to 0. These are often called eigenvalues for reasons that will become clear when we talk about systems of equations, because then that will actually be a matrix. And so these are the eigenvalues of some corresponding matrix, which is why we often call them eigenvalues. And if for some I and for all j, we have lambda I is greater than or equal to lambda j, then lambda I is a dominant eigenvalue. Because it's larger in modulus than any one of the other ones. And of course here, this isn't just the absolute value, this is modulus, because you can have imaginary and complex eigenvalues. Or if this inequality is strictly greater than lambda j, then lambda I is the strictly dominant eigenvalue. And this is quite important because even if you don't fully solve a system for the solution of a higher order linear difference equation or differential equation, you can often understand the overall behavior of the system just by looking at the dominant eigenvalues. So asymptotically, the behavior of a typical solution to the system, or to the difference equation, typical solution, not system, is controlled by the dominant eigenvalues. For example, if it turns out that lambda I is a dominant eigenvalue, and we know that lambda I, the modulus of lambda I is less than 1, then solutions converge to 0. Okay, that's all for this video. If you want to see a bit more detail on this material, stay tuned for the next video, which will expand this and do a little bit more review of some of the differential equations, as well as some examples of how this can be applied. Yep. See you in the next video.